Okay, so this it should be, I'm hoping, the last in section 3.2 of the video. Let's get started. Let R be an equivalence relation on the set A. So you should know what that is now. Equivalence relation is something that's it's reflective, symmetric, and transitive. For X belonging to A, the equivalence class of X determined by R is the set X over R, which equals Y belonging to A, such that X relates Y. And I think I said X over, it's actually X mod, which we'll talk about the terminology in a minute, how you say it. So when R is fixed, okay, throughout a discussion, or if it's clear from the context, then we usually use the notation, so sort of this, bracket X or X bar, and that's used instead of X mod R. And X, that bar there, is not divides or anything. It's read as the class of X modulo R, or simply X mod R. Okay. And so the set A mod R is equal to also X mod R such that X belongs to A. So this is the set of all equivalence classes called A modulo R. Okay, so that's the set of all equivalence classes. All right, let's look. Oh, I guess I'm supposed to do example 3 here. Oh, I didn't leave what's, just part A. Okay, so let's look. This is our relation H, okay, so this is on the set 1, 2, 3. Remember, on means A cross A then, right? And so this is an equivalence relation, and you can quickly look at it to make sure it's an equivalence relation. We have, for every element, there's 3 elements in A, and they all should, for all elements in A, in order for it to be reflexive, it has to reflect itself. So 1 relates 1, 2 relates 2, 3 relates 3. Symmetric if X relates Y. So if 1 relates 2, then 2 must relate 1. And of course, it's trivial for these, right? If 1 relates 1, then 1 relates 1, right? Transitive property. If you can set up a transitive property, let's see, can we set one up? Well, 1 relates 2, 2 relates 2, so 1 relates 2, right? And then 2 relates 1, 1 relates 1, 2 relates 1. Okay, so if you can set it up, and it works out for every one you can set up, right? Then it's transitive. So you can see it's an equivalence relation. I mean, besides the fact it's just stated it's an equivalence relation, we can verify that as well because the relation is not that big. Okay, well, here's the thing. So let's talk about what 1 mod R, 2 mod R, what would it look like? Well, if we go back to the definition of X mod R, then it's the Y belongs to A such that X relates Y. So X is coming from your A, right? X is coming from A, okay? And it says that here, so X is coming from A. So we have 3 elements in X, right? 1, 2, and 3. So here we see that 1 mod H will equal, well, what does 1 relate to? Well, 1 relates to 1, but it also relates to 2. So it's the set containing 1, 2, right? Well, what about 2 mod H? Well, 2 relates to 2 and 2 relates to 1. Interesting. And then 3 mod H is just 3 relates to what? 3. Because remember, these are just your Y values that comes from, so X relates Y. So here we see that 1 mod H actually equals 2 mod H. Right? You guys see that? So 1 mod H equals 2 mod H. And so therefore, A mod H in this example, well, remember A mod H, so A is representing all the set of equivalence classes. Well, it's just going to be the set containing 1, 2, and then the set containing 3, because we know in set notation we don't repeat sets. We don't repeat elements, right? Okay. And so that set right there, that set 1, 2, the set containing 1, 2, that took care of 1 mod H and 2 mod H, and then the set containing 3 took care of 3 mod H. Okay, so hopefully that made sense. Okay, so if you want, you can pause and write this down and then listen to the video. I'm just doing this to save time. So look at the second example here, and we see, okay, so we see here, I've just gave you some examples of what, and I used the different notation to represent our equivalence classes. But just looking at this first example, oh, that's an erasure, okay. Just looking at this first example here, well, how did I come up with that? Well, here's the thing. Going back and always understand what the definition of X mod R means, right? So going back to this definition here, X mod R is equal to a Y and A such that X relates Y. So here we can say, well, this is the same thing as saying 2 mod S, right? And so that is where there's a Y such that we know, so 2 mod S, there's a Y such that we know 2 squared is equal to Y squared. Well, if we solve for that, so Y squared is equal to 4, to put the square root on both sides, so Y is plus or minus 2, right? And in fact, that's going to be the case for every real number that we take, well, except for 0, right? Well, 0 is just going to be one element there, okay? And so we're going to have an infinite amount of equivalence classes, right? Because we're on R cross R. So when you have an infinite amount, you have to annotate that. And so we're going to have here R mod S is going to equal the set containing X negative X, and for 0, I mean 0 negative 0 still 0, right? So it still works for 0 as well, such that X belongs to R. So that is the set of equivalence classes for that, okay? Okay, so looking at 3C, and you have it in your notes, we have this relation R where it's Z cross Z such that X plus Y is even. So I want you to take a minute and figure out the equivalence class for 0 mod R, 1 mod R, and 2 mod R. Okay, well, you should have discovered something very interesting, is that the even numbers here, the even integers, they're going to have the same equivalence class. And I would bet that if you did the I 3 mod R, 5 mod R, they would have the same equivalence class as well. So what we know is that the final answer will be what? Okay, so you figured it out then. There's only going to be 2 equivalence classes. And if we let E equal the set of even integers and D equal the set of odd integers, then Z mod R is just going to equal the set containing D and E. Which leads us to a great fact about equivalence classes. Okay, and that fact is that equivalence classes are either equal or disjoint. Okay, and if you go back and look at the other examples, that satisfied the condition. Okay, so let's look at this theorem 3.21. So let R, and again, you can pause the video and write this down. Let R be an equivalence relation on a non-empty set A for all X, Y, and A. Then we have the first statement is X mod R is a subset of A and X belongs to X mod R. Okay, well, that, we haven't even talked about the proof, but that sort of seems straightforward, right? Because in equivalence relation, it's reflexive. And so X will always relate to itself. So that sort of seems like a straightforward proof. But what this tells us is that every equivalence class is a non-empty subset of A. B, X relates Y if and only if X mod R equals Y mod R. And that's telling us that elements of A are related if and only if their equivalence classes are identical. And then X doesn't relate Y if and only if the intersection of X mod R and Y mod R is equal to the empty set, okay? And so this talks about elements of A are unrelated if and only if their equivalence classes are disjoint. So I'm not going to waste time in this video to go over the proof because it's in your book. So I want you to actually complete this proof in your book, from the book, and have these by tomorrow. Okay, so I have to make an addendum here. When I did these notes, this was back when I had the other edition book. So I see that they changed this theorem number. So this is actually theorem 3.22. And so that's the proof. And they use different notation too. So remember, X mod r is the same as x bar. So they're using x bar and y bar to talk about equivalence classes, but you have all the same, it's the same notation. So go ahead now. So prove theorem 3.22. Okay, so I'm trying to stand at 15 minutes. So let's see. I'll stop it at 15 minutes regardless. And what I don't finish from the notes today, I'll wait. We can work on that for Wednesday's class, okay? Because I do want to just try to do 15 minutes for each class and then have you guys work on problems. So, definition. Let m be a fixed positive integer. For x, y belonging to z, we say that x is congruent to y modulo m if and only if m divides x minus y. And we write this as x congruent to y, and that little m there refers to our modulo, or x equals y mod m, which this is the usual notation I will probably use, but either or is correct. And so the number m is called the modulus of the congruence. So let's look at this example. Well, 3 is equal to 6 mod 3. Since 3 divides, so your m is here, and then this is your x, this is your y. So since 3 divides 3 minus 6, which is the same thing as saying 3 divides negative 3, and we know we can, by definition, that means negative 3 is equal to 3 times some integer, and that integer happens to be negative 1. What about 4 equals 1? Well, that is 4 equals 1 mod, 3, right? Since, 3 divides 4 minus 1. All right, so that's 3 divides 3, and that's 3 equals 3 times 1. Okay, so this is not right. Theorem, this number will change. Let me look at so the new number is, so it's 3.23 is the theorem for this new one. And it says for every fixed positive integer m, congruent m is an equivalence relation on z. Okay, so this is the proof, and I'm going to show reflexive and symmetric because I really want to keep the minutes down to 15 minutes. I want you to finish. I'll make another video, but it won't be for you to watch before Tuesday's class because I want to make sure the people who did not watch the other 2 videos watch those other 2 videos. But here we go. Let's start. So let m. Reflexive, again, as always, can be tricky to prove, but we're trying to show that on this congruence, that's our equivalence relation, that this is that it is an equivalence relation on the integers. So let m be a positive fixed integer, right? So we have to show that x equals x mod m, right? And that means m divides x minus x, right? And so if we think about it, what it's really saying is, well, x minus x equals m times some integer, right? Well, x minus x is just 0, so 0 equals m times 0. So interesting. So that's why we say, well, let x be an integer. M times 0 is equal to 0, which is equal to x minus x if we rewrite, right, that form. So therefore, we say that m divides, that should be x minus x. And thus, this equivalence. This is reflexive. This congruency is reflexive. This modulo m is reflexive on the integers. Symmetric. Let's look at symmetric. Well, let x and y be integers. Suppose is an if-then statement, right? So suppose your if. So suppose x equals y mod m. All right. So that's, again, the definition of what that relation is. We have to show that y equals x mod m, which means m divides y minus x. And you know that means y minus x equals m times some integer z, for some integer z, right? And so that means m divides x minus y. Now, the show part is not part of our proof, right? So I'm going from the suppose. So suppose x equals y mod m. That means m divides x minus y. So x minus y is equal to m times some p for some integer p. And I sort of did like a fill in the blank. So x minus y equals m times p. Well, if we multiply both sides by -1, which we can do because it's an equation, then we get negative times the quantity of x minus y equals negative mp. Well, we know right there that that's, if you distribute that through, that's negative x plus y, which is the same as y minus x, which is what we wanted in our show part, right? And so that means y minus x is m times some times negative p. Well, since p is an integer, negative p is an integer, there m divides y minus x. Hence, this modulo here is, modulo m is symmetric on z. Go ahead and finish transitive property, and I will see you in class tomorrow.